Okay. So today we'll talk about edge coloring, which is somewhat similar to what we've been doing with vertex coloring, although it's a little bit different. Okay, so now instead of coloring vertices, we're going to color edges. So proper K edge coloring of a graph G. Well, it's a coloring of the edges with K colors such that some condition holds. So it's a map or a function f from the edges of G to K colors. We can just call them 1 up to K, such that if E and E prime are edges such that they're distinct edges, so E is not equal to E prime, and E and E prime share an endpoint, then in the coloring they have to get different colors. Okay. Yeah. So now the goal is to color the edges with as few colors as possible, such that when edges intersect, they get different colors. So in other words, like, if you think of all the edges that have a particular color, they form a matching in the graph, right? So you can also think of this as decomposing the edge set into matchings. So it's equivalent to decomposing meaning partitioning E into K matchings. Right? Okay. Because the edges of any particular color must be a matching. Oh, and another definition. So you have something similar to the chromatic number for edge coloring. So it's usually called it's either called the chromatic index. So the chromatic index or edge chromatic number. Of G. So both of these terminologies are used quite often. And it's exactly what you expect it to be. It's the minimum number of colors. So, okay, the notation is chi prime of G, which is the minimum K such that G has a proper K edge coloring. So minimum K such that there exists a proper K edge coloring of G. Okay. Now, okay, so in a certain sense, this is a new concept, different than this vertex coloring that we've been talking about for the last few lectures. But in another sense, it's sort of almost, well, not the same thing, but it's a kind of special case of vertex coloring. If you take the graph and you think about its line graph, right? So let me give this definition. So So given G, the line graph of G is the graph, so I'll call it L of G, with vertex set E, so E is the edge set of G, and edge set so literally the kind of condition that I'm talking about in this definition over here. So you take all the pairs E, E prime, where E and E prime are edges, they're distinct, and so I'll write it like this. So their intersection is non-empty, meaning that they have a point in common. They have an endpoint in common. Right, so note that, so this so-called kind of new concept we've defined here, this chromatic index, it's nothing more than just the usual chromatic number applied to the line graph. So chi prime of G is the same thing as chi of L of G, where this is coloring vertices of the line graph, which is the same as coloring edges of the graph. Right? So in particular, anything we proved so far about edge or vertex colorings also holds for edge colorings. But edge colorings have some nice kind of interesting features which are quite different from vertex colorings. So because it's a kind of special, it has some kind of special properties. It's a special case of vertex coloring, right? But are there any questions up to this point? Okay. So here's so we focused in vertex coloring on some of these trivial upper and lower bounds. So for edge coloring, you also have another kind of trivial lower bound that the chromatic index is at least as large as so delta of G, which is the maximum degree in the graph. Right, and the proof is kind of simple. So if V has degree delta of G, then all edges containing V, they all have to get different colors. Right? And so globally, in total, you have to have at least delta colors, because even just to color the edges coming from that particular vertex, you need delta colors. So you certainly couldn't do it with less. And this is kind of the same thing as this other trivial lower bound. So note, so it also, if you think about the line graph, this follows from saying that, so the chromatic index of G is, like we said, the same as the chromatic number of the line graph of G, which is at least the clique number of the line graph of G, which, if you think about it, it's easy to see that this is at least the maximum degree in the graph, in the original graph G, right? So this proposition is sort of something we've already seen before, in a certain sense. And note that these things are pretty much always equal. There's only one tiny case where they're not, but that's not terribly important. Okay, so here's the first kind of interesting theorem. So this is called Koenig's edge coloring theorem. It says that this trivial lower bound is actually tight if G is bipartite. So if G is bipartite, then the edge chromatic index, or sorry, the chromatic index or edge chromatic number of G is simply equal to the maximum degree. So, okay, any questions about anything? Anything not clear? Okay, so the proof of this is actually going to be, so you can prove this kind of from first principles, directly, but given that we've built up a lot of different, theorems, you can actually prove this like quite quickly, given what we did yesterday and what we did on Wednesday. So last Wednesday, we proved. So if you, I don't expect you to remember anymore, but yeah, we proved that basically. So if you take the line graph of G, the complement of it is perfect for every so for G being bipartite. So you might remember that this was just an application of the original Koenig theorem, right? And so, so now by the weak perfect graph theorem that we proved yesterday, this means that the line graph of G is perfect because a graph is perfect if and only if its complement is perfect. So therefore, in particular, you have that the chromatic number of this graph equals the clique number of L of G equals the clique number of L of G. Okay, and this proves the theorem because this is equal to max degree in G, and this one is equal to the chromatic index of G. Okay, but you can also, like I said, it would take a little bit longer, but you can actually just prove this directly if you like. But it's nice that given what we've proved already, you can just get this really short proof. Okay, so what I want to focus on for the rest of the time today is something called Vizing's theorem. Which says that, so we had this trivial lower bound for every graph that it's at least the maximum degree. And for bipartite graphs, we know that it's actually equal to the maximum degree. And Vizing's theorem says that actually, so if you drop this bipartite condition and you look at every graph, it's not that far away. This edge chromatic index is not that far away from being just the maximum degree. So for every G, so for every graph G, not necessarily bipartite or anything, you have that the chromatic index of G is at most the maximum degree plus 1. Okay. So that basically, if you think about it, we know it's at least the maximum degree. If this tells us it's at most maximum degree plus 1. So that means for every graph, we have this weird thing that, the chromatic index it's narrowed down to just 2 possible values. Like it's either delta or delta plus 1. There's no other possibility. So you might think that this makes the problem easy, but I just want to kind of have a side note. So even though we've got it down to just 2 possible values, so the problem of determining whether the chromatic index is equal to max degree turns out to be NP complete. So we've got it down to 2 possible values, but it's quite hard to decide which one is the real answer. Okay. So Okay, so we're going to prove this theorem now. So, so we're going to prove it by induction on the number of edges. Okay, where the base case, is kind of trivial. So base case, where, for example, if you have no edges, is trivial. So we just need to do the inductive step. Okay. So now we just consider any graph, and we want to use induction, so we're going to need to, reduce this to a graph with fewer edges. Okay, so as a first kind of natural step, what you can do is you just pick any edge and delete it and see what happens. Right? So I've got these two vertices, v and y1. I let vy1 be any edge. So you'll see why I called it y1 later. And let g prime be the graph where you just take g and delete that edge. So this notation, when I write this notation, g minus the edge, I just mean it's the same graph except I removed that one edge. So by induction, there exists a proper edge coloring of this graph using, so there exists a proper so this is mapping all the edges except for one we deleted to the numbers 1 up to delta plus 1, where so delta is going to be a shorthand for delta of g. Right. So this is a proper edge coloring of g prime. Okay? Because, by induction. Okay. What we want to do now is try, so this gives you a way of, so this coloring F gives you a way of coloring every single edge of G except for one, right? The edge VY1 is not colored, but everything else has a color, and it's a proper coloring, proper edge coloring. Okay, so a kind of key definition. So say that a color C is free at a vertex W if so none of the edges containing W are colored with C. Okay. Okay, so that's kind of natural definition. You just, at any vertex, if a color doesn't appear on its edges, you just call it free at that vertex. Now, a simple observation is that every vertex has at least one free color. Right? Because the number of colors is delta plus 1, and the number of edges containing any vertex is only at most delta. Right? So So in particular, at the vertex V, so remember we deleted the edge V, Y1. So at the vertex V, there's some free color. So now, so this is going to have be a kind of special color. So I'm going to give it a special name. So red. So it's hard to see the colors, I think, on the board, so I have to write big. But so let red be a free color for V. Okay, so now, so what we're going to do now is as follows. So you have this vertex V, you have this vertex Y1, and you know that everywhere else, so let's say white means that this edge doesn't have a color, and everywhere else the edges have colors, and it's a proper coloring, right? So what we're going to do is we're going to try to color this edge with red. So I'm just going to put red there, kind of carelessly, even though it causes problems. So we color VY1 with red. Now, obviously, yeah, this can cause problems because, well, so one thing is, this doesn't cause any problems at V, right? Because red is a color that's free for V. So all of the other edges coming from V have different colors, so none of them are red, right? But it can cause problems at Y1. Okay, so of course if it doesn't, then we're just done, and we found the coloring. So therefore we assume that Y1 already has a red edge, and this is why this isn't a good coloring. But remember, I mean, Y1 has a free color, right? So we're going to try to, so we're still going to try to make this red, and we're going to try to switch this one to a free color for Y1. Okay, so let C1 be free for Y1. And yeah, we're going to try to change this one to color C1, right? But obviously that causes problems because maybe this guy has an edge of that color. But we're going to try to make that one red because after we color this one, okay, let's just call it blue. So after we color this one blue, this guy no longer has a red edge coming from it because we've colored this one blue. So I can try to color this one red. And again, it causes a problem. Well, maybe this picture gets confusing, but again, anyway, I'm trying to color this one red. It again causes a problem because there's already red here. So I try to color it blue, and so on. Okay. So we basically try to switch the colors red and blue on some sort of path that starts from Y1. So to make this formal, let me say, so let P1 be a maximum length path starting at Y1 with colors alternating between, red and C1, which is blue. Right, so, okay, so where the first one is red, right? The next one is blue, and so on. And now, suppose that this path ends somewhere in the graph which is not V. So if this path doesn't end at V, then what we're going to do is we're just going to switch along this path, kind of like how we dealt with augmenting paths in matchings. So yeah, so the first edge used to be red. We're going to make it blue. This one red, blue, red. And if this path doesn't come all the way back to V, then basically at this point we'll be happy because now you're not going to have any conflicts anywhere. Right? Because kind of by assumption this vertex doesn't have any red edges coming from it, otherwise you'd extend the path. And every vertex has the same colors on the edges around it, except for this one, who now has a blue one instead of a red one. Okay. So, right. So if P1 doesn't end at V, then we swap the colors red and C1 on P1. I should have maybe clarified, this path P1, it's not using this red edge, it uses the other one, right? That's, yeah. Okay, so therefore, we assume that, so we suppose P1 ends at V. So now the picture looks like this. Something like that. So you know that, by the way, you know that the last edge of P1 that goes, so the one that goes to V has to be blue, right? Because red was free at V, right? So this really is what the picture looks like, except obviously this could be longer, but this is the idea. Okay. And we're going to let Y2 be the second last vertex of P1. So Y2 is this guy. Okay. So now what we're going to do is basically we're going to give up. First of all, we're going to give up on coloring this red. Right? That seems like a lost cause because, you know, you have this sort of chain reaction. If I color it red, I have to make that one blue, I have to make that one red, etc. And then I have to make this one red. Which would conflict with this one because this one is red, and then I have this kind of chain reaction going again, right? So I'm going to completely give up on coloring this one red, and instead I'm going to look at this one and say, okay, I'm going to color this one red. So now we try to color VY2 with red. Okay. And when we do that, we know that the color blue is free for Y1. So basically I'm going to take this edge that's blue, I'm going to take the blue away. I'm going to try to make it red. And since I've given up on making this one red, I'm going to make this one blue, which is perfectly fine because this blue is a free color for Y1. Okay. So once we've given up on making this edge VY1 red, so we now color VY1 with this color C1, which in the picture is blue. And we try to color well, why don't I not just say try, but so we recolor the edge from V to Y2 with red. Okay. Now, obviously, it causes a conflict, meaning you have a vertex with two red edges. I mean, actually, in this picture, you can literally see that y2 has two red edges. It's basically by construction, so it's looks like quite bad news. But basically, what we're going to do now is do the exact same process, except starting at y2. So let C3. So let C3 be a color that's free. Oh, sorry, not C3, C2. For Y2. And such that C2 is not equal to C1, which we can do because actually, if you think about it, Y2 has two red edges, so it actually has two free colors. It actually has at least two free colors. So even if the color C1 happened to be free for that vertex, it also has a second one. So we can do this. And basically we do the same thing again. So let P2 be a path. So be a longest path starting at Y2 with colors alternating between red and C2, which is purple. And so where the first edge of the path is not Y2b, right? So we take the other red edge and we do that. So again, if this path doesn't end at V, then we're just going to switch the colors to get a coloring. So let's see what I can do. All right, so this path, so it starts with Y2. It uses a red edge, and then it uses a purple one, and then it switches back to red. So we took the longest such path in the graph. If it ends at some other vertex of the graph that's not V, then I would just take the first edge, make it purple, take this one, make it red, purple, etc. And when that terminates, you'll have a proper edge coloring, and you'll be done, right? Because this was the only conflict in the whole graph, that will be resolved, and you haven't made any new conflicts. So therefore, this one must end at the vertex V. But that picture can't happen because the last edge can't be red because red was free at V originally. So the last edge is a purple one. Right? And then we just do the exact same thing again. So we label this vertex Y3. Right? And basically, we're just, so the proof, the way that the proof goes, like kind of at a high level, is it just says, keep doing this, keep doing this, keep doing this. Eventually, it has to stop because every time you do this, you find a new neighbor of V, and V only has finitely many neighbors. Right? So these vertices Y1, Y2, Y3, etc., end up being distinct. But let's do the details. So, but are there any questions about anything so far? Okay, so right. So if P2 doesn't end at V, swap colors on P2, and then you found the coloring you were after. So so P2 ends at V. So we let Y3 be the second last vertex of P2. And note that the edge VY3 was color C2, which is purple. Okay. And again, you take some color which is free for C3, you call it C4. You do this kind of alternating path thing. It again ends at V. You find another neighbor of V, and so on and so forth. Yeah, so let me kind of just show one more step of this, because there's a subtle thing that happens at this point. So, right, so there's one thing that hasn't kind of appeared yet in this proof, which appears now. So we let, we define, so you define C3 kind of the same way as before. It's a color that's free for V3. You define the path P3, Y4, as above, right? So, or analogously. Right. Now, I want to claim that all of these vertices, so I want to know that these vertices are all distinct. Because remember, that's where the contradiction comes from, right? The contradiction comes from finding, you find a whole bunch of distinct neighbors of the vertex V, and that can't go on forever, right? But is it clear that these things are distinct? So for example, what if I should also say that I've chosen this color C3 again. So this is actually turns out to be slightly technical but important. So I've picked that one to be not equal to C2, which you can do because it has two free colors and so on. But okay, so yeah, so could it be the case, for example, that Y4 equals Y1, right? Because if that was the case, then this whole argument would break down, because I haven't found lots of distinct neighbors, right? And I claim it cannot. So if it were, then, well, so then we must have that. So I'll explain this in a second, but so the color C3 would have to be equal to the color C1 because the edge VY1 is currently colored with C1, right? So, and the last edge of P3, so the third path, was color C3, right? So if so the last edge of this path, right, goes from the vertex V4 to Y4 to V. We know that that color of that edge must be C3, and so if it was equal to C1, right, we know it also has to be C1, so these colors would have to be the same color. So this is kind of a technical point. It's kind of the most annoying bit of the proof. But now, if this was to happen, we can actually get a contradiction. So perhaps it's good to show with a picture, actually. So let's go through the kind of details of what happens. So, right. So at this point, this is right when we changed the color of this one from red to blue. We changed this one to red. We tried to make this one purple, and we had this kind of alternating path that ends at Y3, right? So at this point, what you do, so this kind of proof strategy I've told you about, is you would give up on coloring this one red. You would instead color it purple, and now you'll try to color this one with red, right? And then now you find this color like we did. So you have this color C3 that, sorry. No, C3 is free. For Y3, so none of the edges from Y3 have that color. And we try to make this one that color. We can't because there's an edge like this. You define this path P3 now that comes, which alternates between red and C3. And if it didn't come back to V, we'd be done. So therefore, it must come back to V. Right? And this is the vertex we call C4, or Y4, I mean. Okay. So what I'm trying to argue now is, like, what if, like, how do I know that this Y4 is different from Y1? Right? This is what we're trying to argue now. So if you see this picture, I mean, if these were the same vertex, then these are the same edges, they have to be the same color, right? So what the picture would look like actually, is if that were the case, if these were the same vertex, right? Now in your imagination, imagine all these green edges are blue, right? Well, if you think about it, so, okay, suppose I just put these vertices to be the same vertex. You'll see that that vertex has two red edges coming from it, right? So that would be a conflict, which would be a contradiction. Obviously, of course, these vertices could also be the same, and so on. But basically, the point is there's some first vertex on which these paths meet, and you would have a conflict at that vertex, but that would be a contradiction. Because this was a proper coloring of everything except for one kind of conflict. Okay, so I know that that's kind of a little bit hand wavy. Yeah, I sort of had two options when presenting this proof. Either I could just write down a bunch of conditions that are hard to understand, and then just prove that you can inductively maintain these conditions, or I could go through it kind of step by step. I decided to do it step by step. But anyway, so, right, so if you look at, so basically here, look at first time the paths P1 and P3 meet, and get a contradiction. Right? So that's obviously not a very well explained argument, but it's, I've written it in the notes and stuff, and you're not really responsible for knowing this whole proof. It's rather complicated proof. Basically, so now it's kind of the end of the lecture, so I perhaps won't write all the proper details of how this finishes, but the basic idea, so to complete the proof, you keep constructing, so show you either find a coloring or you can keep finding neighbors, say y1, y2, etc., of V, which are distinct, but that'll be a contradiction because V only has, finitely many neighbors. Okay, so see you tomorrow.